All right. Hello, everyone. I'm Ben Sachs, and this is a talk on handling a whole bunch of different kinds of hardware, a whole bunch of different similar hardware devices with a single implementation using templates. There's a lot to get through here, so let's dive in. I guess I will say, for those of you who don't know me, my company, Sachs & Associates, offers training in C and C++, particularly for the use in embedded systems to companies all over the world. And to start off, just some basics. So in general, we communicate with hardware devices via what are called device registers. And for modern hardware devices, those are often memory mapped device registers. That is, the hardware is built in such a way that each device register that's associated with a piece of hardware is assigned an address in the program's memory space, and then you can access it as if it were any other object in memory. So you'll have part of your memory space that's the actual physical memory, RAM, ROM, flash, whatever it is that you have, and you'll have some other piece that is your memory mapped register space. And then when you want to talk to one of those memory mapped registers in C and C++, you can go ahead and create a pointer that points to the appropriate location and then assign to the register by writing through that pointer, or read from the register by reading through that pointer. You can just as easily use a reference. Either one will work just fine. So in most cases, devices are made up of multiple registers. So for example, here I'm showing you the layout for a serial port on a board called the ARM Evaluator 7T. And the board has two of these serial ports that use the same 6-register layout. And the two serial ports basically function the same. So it's perfectly fine in this case if we can create a single class called UART, just another name for a serial port, that contains the data members for our different device registers and has a constructor and appropriate member functions for dealing with a serial port type object. And then we can simply create two different serial port objects, two different UARTs, one at each address that's used by a serial port. And we can use the same type to talk to both serial ports. And when they're the same, that works great, but they're not always the same. So the example I'm going to be using today comes from the Arduino Mega 2560, which has 6 programmable timers, 2 of which are 8-bit timers, and 4 of which are 16-bit timers. And then there are other differences besides that we'll get into. Now, we'd like to be able to write our code using any of these timers, either alone or in combination. But ideally, we don't want to have to write 6 different classes, especially because those classes are probably going to do fairly similar things. We don't want to have to maintain more code than we need to. So what I'm going to be talking about today is a way of writing a single template-based implementation where we extract the differences between the different timers into traits as a way of maximizing the amount of common code that we share and doing so in a way that doesn't negatively impact performance. By the way, I'm using a particular technique for creating my class interfaces here that's based on last year's CppCon 2020 memory mapped devices as objects talk. But the focus of this session is really on ways of writing generalized implementations for families of hardware devices. So the interesting thing is about capturing those differences between different kinds of timers or other hardware devices. And those techniques should apply equally well, whether you're using the techniques from this talk or some other way of representing your memory mapped objects. All right, so as I said, there are 6 programmable timers on the Arduino Mega 2560. And since they're all timers, they support a lot of the same options. They can count up or down. They can trigger interrupts at various points. They have different options for how quickly the timer counts, ticks if you prefer. But there are also a number of differences between the timers. I mentioned that 2 of them are 8-bit timers, timers 0 and 2, interestingly enough, are 8-bit timers, whereas 1, 3, 4, and 5 are all 16-bit timers. But there are also differences that aren't just down to the bit size. Timer 2 uses a different set of clock select options, speed options for counting in the timer than all of the others. So what we're going to try and do in this situation is create a single implementation, a single class template that can cover lots of different variations in the hardware. Now, there are lots of different ways that we could configure these timers, but what I'm going to be focusing on here is we're going to set the timers up so that they start from 0, count up to a maximum value. They trigger an overflow interrupt. When they hit their maximum value, they will send an interrupt signal. Then they'll restart counting from 0, and eventually they'll reach that maximum value again and overflow again, triggering another interrupt. Okay, so here is where we are going. The user of these timer types will create an object of some timer type, like say timer 0 here, at a specific address. When they do, they'll specify 2 things: how quickly they want the timer to count as an enumeration value, and we'll talk about what the options there are going forward, and the maximum value. How high does the timer count before it starts over from 0, triggers the interrupt? So as I mentioned before, we can create the timer and access it through either a pointer like this or a reference. What you will see me do in these notes is use the reference notation because it makes the timer, the memory mapped object, look a little bit more like an object that's really at that location, which is what we would really like to have. So in addition to creating the timer objects, the user is going to be responsible for writing the interrupt handlers. So the Arduino makes this fairly simple. It has a packaged library that's automatically registering a default handler for each interrupt. And it's chosen a predefined name for every one of those interrupts. So your job, if you want to replace that default interrupt handler, is you simply need to use this ISR macro to redefine the function, giving it the same name that the library has assigned to it. And the library will take care of the rest of actually setting it up so that the hardware points to it in the right places and will call the function when the interrupt actually occurs. So timer 0's overflow interrupt is called timer 0 OVF vec, just overflow vector. And so we would go ahead, if we want to write an interrupt handler for this, we simply use this ISR macro. It looks pretty much like defining a function, just with a slightly different beginning. And then here's a simple version of an interrupt handler that just counts the number of times that the interrupt has occurred. Could be lots of things. That's just a simple example here. So we're going to build up by starting from a class that is not a class template at all. It's just going to handle timer 0. Then we're going to expand that into a class template that handles both of the 8-bit timers, timer 0 and timer 2. And then we'll expand from there into a class template that works for both the 8-bit and the 16-bit timers. So let's get started. Here is the layout for timer 0. It's made up of these 5 registers. They're located at the address 44 hex. It consists of 2 control registers, a count register, which is just where the timer is storing the count that's constantly counting up towards 250 or whatever maximum value we specified. And then a couple of output compare registers, as they're called, which are values, other counter values that can be used to trigger events, to specify when certain events should occur on the timer. And in this case, we're going to be using one of those, output compare A, that will be designating our maximum value in this case. So our timer 0 class is going to look something like this. It will have 5 private data members of type UIT volatile. So hardware registers, we want them to be volatile objects so that they're not optimized incorrectly by the compiler. They're all 8-bit values, so UIT should work fine to represent them. Now, there's also, it turns out, a 6th register that's associated with timer 0, but it's not actually located with the other registers in this hardware. It's at a separate location. It's called the interrupt mask register, and it controls which timer 0 events are set up to trigger interrupts, which ones are enabled to actually send interrupt signals. And that's located at hex address 6E here. So I'm representing that right now as a separate object that is a reference to a single volatile UIT. We have going along with that, the bits in that register represent the different interrupt sources that the timer can trigger, can report. The one that we're interested in here in this case is the overflow interrupt, but there are others we could use. And what we will do is timer 0's constructor, among other things, will be responsible for setting the correct bit in the interrupt mask register so that timer 0's overflow interrupt is actually enabled, and the timer will actually do something when it overflows. Okay, so the first argument to timer 0's constructor is the counting speed that's chosen by the user. This was an enumeration type that I showed a little bit before. Now, the counting speed is determined by 3 bits in the control register, in control register B here. And timer 0 has a few different options. It has 5 predefined counting speeds based on the system clock that you can use, just multipliers of the basic system clock. Or you can specify an external clock source that will be determined when timer 0 ticks, counts. So here we have an enumeration type that represents that list of options. I'm calling it the clock select because that's how the documentation refers to it. And generally speaking, when I'm dealing with hardware documentation, it's hard enough to understand in some cases anyway. Using the names from the documentation seems like the best way to minimize any confusion. So other than the clock being just completely off, we have our 5 different speed settings that are based on the processor speed and 2 different options for an external clock, falling and rising edge. Our second argument to the constructor is that maximum value, what the timer is going to count up to and where it's going to overflow and restart. As I mentioned before, that value is going to go directly into the output compare register A. So the constructor will simply take that value and assign it to that register. One other thing, there are a couple of other configuration aspects of the timer. I mentioned that we're going to set up the timer so that it counts up to a configured maximum value. These two constants here are setting a few additional bits in timer registers, in the control registers A and B, that I'm just going to gloss over for the purposes of this talk. You can use them to configure the timer in other ways, but they're not really interesting for what we're trying to accomplish here. All right, so now let's take a look at the timer 0 class. All right, timer 0's constructor takes a clock select option and a maximum value. We saw this earlier. This is what the user will specify. There's only one timer 0 object in hardware. It only makes sense to have, there's only one piece of hardware for it. So we probably don't want timer 0 to be a copyable object. Makes sense to turn those operations off because copying it should never happen. We have our other public member function, because most of what timer 0 is doing is really setting up the interrupt trigger. And then that's in some ways, the interesting thing. But our other public member function is the get count function, which just tells us what's the timer's current counter value. It lets us know how close we are to that maximum value and when we're next going to overflow. So here is our timer 0 class. The clock source enumeration is a public member so that the user can choose one of those options to pass into the constructor. We have our deleted copy operations and our get count member function. And then the storage, the private data details are, we have the enumeration that tells us how to enable the different interrupt sources, like the overflow interrupt for timer 0. We have those two mystery constants that I mentioned earlier that are other miscellaneous configuration. And then we have the 5 data members that make up our timer hardware. Okay, so the implementations of these functions look like this. We have our interrupt mask 0 register here defined as this single separate object outside of the class because it doesn't fit the same layout. The constructor simply takes in the clock select option and the maximum value. It sets those extra configuration bits, count mode A and B. The control register B is also where we configure the clock select. So we combine those bits together using the binary OR operator. The maximum value simply gets placed in output compare register A. That will be used as the maximum based on the way that we've configured the timer. And the only other thing to do is enable the overflow interrupt. Okay, get count at this point simply returns the counter value. It's about as simple as it gets. So that's our basic starting point. Now let's talk, how are we going to build on this thing and go from the state that we have right now, where the user can create an object that lets them access timer 0 like this, but this will only work for timer 0. And if they create this timer and define a corresponding interrupt handler, they're set up to use timer 0. But we want them to be able to use not just timer 0, but also other timers. And in this case, we're going to focus on adding support for timer 2, the other 8-bit timer. So we're going to turn our timer 0 class into this timer 8t class, or class template, I should say. And it's going to take this template type parameter, timer traits. Now, what is a timer traits? It's some type where the members, the traits, as we say, of that type describe differences between timer 0 and timer 2, ways in which they are similar, but not quite exactly the same, and the implementation needs to do slightly different things. So when we're finished, we'll have these two different traits types, timer 0 traits and timer 2 traits. We'll be able to use them to create timer types, timer 0 and timer 2, by specializing our class template with the appropriate traits object. And then the user will be able to just go ahead and use either timer 0 or timer 2. But our job will be just to maintain this one class template, the timer 8t template, rather than maintaining two separate classes, even though their implementations are slightly different. So what are the differences between timers 0 and 2? Well, there are two major ones that we're going to deal with. One is the location of the interrupt mask register. Just like timer 0, timer 2 has a location in memory separate from the rest of its device registers that describes which interrupt sources timer 2 is allowed to trigger. They also support different counting speed options. You may remember that in the table before, back at the beginning, timer 2 was the one that had different counting speed options from the rest. But otherwise, they're fairly similar. They have the same register layout. They support the same interrupt sources. So this was timer 0's interrupt mask register located at hex 6E. Timer 2's interrupt mask register is located just a little ways away at hex 70. And it just has a very similar name. To use either timer, we have to enable the bits in the corresponding interrupt mask register. So that difference in location, where the interrupt mask register is located, that becomes our first trait. So we're going to add a member to each of our two traits types, timer 0 traits and timer 2 traits. That's a static data member that's a reference to a volatile uint t, that is the interrupt mask register that goes with this timer. And in timer 0, it will refer to the location hex 6E. In timer 2, it will refer to the location hex 70. And that will let us go from this constructor for timer 0, which knew specifically how to enable the overflow interrupt just for timer 0. It was fixed when we wrote this code that this line of code was going to be talking to the interrupt mask register for timer 0. And our code is going to change from this into this. So the red is highlighting the differences here. It's now a class template, so we have the template boilerplate at the top. The name of the class is now slightly different, so we need to refer to it that way. But the difference, the thing that's actually making the implementation do the right thing for either timer 0 or timer 2, is this piece. We refer to the interrupt mask register as something that is a member of the timer traits object, or timer traits type, whatever type is passed in as the template argument. So when we specify either timer 0 traits or timer 2 traits, we'll get whichever value is appropriate for that timer. So this table here, pretty simple right now. This shows the differences in our traits that our traits types are currently reflecting. And right now there's just the one difference in the location of the interrupt mask registers, but we're going to go ahead and add more on going forward as we support new traits and additional timers. The next trait to deal with is the counting speed. So I mentioned before that, well, I should say, timer 0 and timer 2 both use the same bits to control their timing speed. It's the same locations in control register B. It's just that the options, the meanings of those bits are different for timer 2. Timer 2 can't be driven by an external source at all. Instead, it just has 7 predefined speeds based on the system clock that you can use, and your selection has to be one of those. For timer 0, we had an enumeration type clock select that enumerated the options, the counting speed options for timer 0. What we're going to do now is we'd like to have another enumeration type separate from that one that represents the different set of options that are available for timer 2. This is kind of like the way that STL containers specify an iterator type as a type member that describes how you can interact with that container. You can step through a vector in different ways than you can step through a list. You can use different counting speed options for timer 0 and timer 2. So in our traits types here, each one will now contain an enumeration type, both of which are called clock select, but each of which has its own set of options. Some of them are the same, but most are different because that's how the bit patterns happen to work in register B, in control register B for timer 0 and timer 2. So now we've added that to our traits table. Now I've labeled timer 2's clock select options as different because if you remember back at the start, I mentioned timer 2 is the only one that uses that set of options. All of the other timers use the same common set of options, hence the common for timer 0. All right, so now we're ready to take a look at the timer 8t class template. It's going to look a lot like the timer 0 class, it's based heavily on that. I've highlighted the differences between them in red. Okay, so it's now a class template, so it's got the template boilerplate at the type, or at the top. The clock select, rather than being an enumeration that's spelled out directly in timer 8t, is now a type alias for whichever clock select type we got from our timer traits. Timer traits is a template type here, or a template type argument. Clock select is a member of that type. That makes it what we call a dependent name. What the clock select is depends on what argument gets passed in for timer traits. And the way that the compiler parses templates and makes sense out of them to try and give you the most helpful error messages that it can, it wants an additional hint from you, this keyword type name that lets it know that clock select is going to be the name of a type as opposed to the name of a constant or something else. That will let the compiler know how it's supposed to make sense out of this piece of code. Otherwise, we have a very similar looking constructor. Now, the actual meaning of the clock select type is now a little bit different because it now depends on our timer traits. But the interface piece looks exactly the same. We haven't changed how the user calls this function or provides arguments to the constructor. The thing is still non-copyable. Timer 0 and timer 2 are going to be separate types, and each one of them, it doesn't make sense to copy. And we still have our getCount function. The private piece of the class is actually exactly the same. There are just no changes here. The interrupt source piece is the same. Those 2 bits of configuration are the same. And we have the same register layout with 2 control registers, a count register, and the output compare registers. So here are our function implementations. We saw a version of this before, but just to reiterate, here is our constructor for timer 8t. It looks very similar. It sets the values in the control registers in exactly the same way, because again, the same bits are being used to represent the clock select in both timer 0 and timer 2. Those bits just have different interpretations. So we want to expose them as different enumeration types to the user. But inside, the implementation doesn't need to change. We're still setting the same bits in those registers. We're still taking using the output compare register A to designate the maximum value. We're now just setting the the bit in the appropriate interrupt mask register based on whatever our traits tell us is the right interrupt mask register for the timer that we're dealing with. getCount, other than the addition of the template boilerplate, remains basically the same. It just returns the value of the count register, the count register for whichever timer we happen to be dealing with. So using this type, we now have this class template. We can now create objects for timer 2, very similar to the way that we created objects for timer 0. So the user can go ahead and create an object of type timer 2, where timer 2 is an alias for a specific specialization of this template, just to make things a little bit easier to read. And it goes at the address associated with timer 2. It uses the clock select options associated with timer 2. So when the user specifies the constructor arguments, they'll make sure to say that the clock select options are the ones coming from this timer type and not a different timer type. But if they get it wrong, don't worry, that they will get a compile error. We'll talk about that in just a moment. And then they also need to, as before, define an overflow interrupt handler for timer 2. And they do this the same way that they did for timer 0 by using the ISR macro to define a function with a specific name. In this case, the name is just slightly different. It's got a 2 instead of a 0. And this can be a completely separate function. And timer 2's overflow interrupt has nothing to do with timer 0's. The user can use the timer 8t class to create both timer 0 and timer 2, both types timer 0 and timer 2, and create objects of both of those types to represent the different timers and define interrupt handlers. And as long as they define interrupt handlers for both of those timers, they can use both timers in the same application. Okay, now, we now support multiple timers, but we're still asking the user to specify the address where the timer is located. So when they create timer 0, they are using placement new here to create this timer 0 object at a specific memory location, which is the memory location that the hardware has designated as being the registers for timer 0. If they do things this way, this all works fine. No problems there. but it would be relatively easy to make a mistake and be creating something, a timer2 object, but accidentally specify the address for timer0. And I know this is an easy mistake to make because I made it while developing this course. So ideally, we wouldn't be able to make this mistake. The user wouldn't have to provide, and the easiest way to avoid that is prevent the user from needing to provide the timer's address. If we can just build each timer so that it knows where it's supposed to go, that's probably going to be the easiest thing for the user to do. So we can do that by adding a third trait to our traits types that represents the address at which the timers are located. So hex 44 for timer 0, hex B0 for timer 2. These are, again, our static data members, constants that just represent the address of the timer. Stood uint putter t here is a type that is an unsigned integer that's big enough to hold a pointer value. It's just it's meant to help you write portable code. So when you need an integer that is at least the size of a pointer, there you go. It's stood uint putter t. So here is our new latest version of the traits table, now with the addresses added in. And how does timer 8, what do we need to do in timer 8t to change it so that it's actually making use of those addresses? What we're going to do is add a class-specific operator new for timer 8t. Now, ordinarily, the keyword new calls a function called operator new, which behind the scenes is responsible for finding a piece of memory that you can use to construct an object of a particular type. When you write x*px equals new x, that use of new is saying, go find a piece of memory that can be used to hold an x object and give me that so that I can construct an x object in that space. Usually, it's pulling that memory from some shared resource like the heap. But in this case, there's only one valid place for a timer 8t or for each timer 8t type to be created, the address where it belongs. So we can use operator new and simply have it always return the same location, the location where things of this type are supposed to go. Since we have an operator new, we should write an operator delete as well. The compiler really prefers these things, the language as a whole really prefers that you pair these things. You can get surprising behavior if you don't. But in this case, the operator delete doesn't actually need to do anything in particular because operator new isn't changing anything's state. It's just always returning a fixed value. There's nothing to clean up when an object of one of these timer types goes away in terms of its memory. So before we had this code where the user had to specify the addresses of the timers themselves using placement new. Our class-specific new means that now we can replace all of that with just this code, which simply uses new timer 0 or new timer 2. And the way that this works is it calls the class-specific operator new function that's defined for those types, which goes and finds and uses the address specified in the traits types to figure out where they're supposed to go. returns back a pointer to that location. The constructor builds the timer object in that location, using the same parameters that it did before. But life is much easier for the user who doesn't have to remember where timer 0 and timer 2 are supposed to go. So much nicer. Now, I mentioned before that there's no danger of mixing up the clock select options. We could mix up the addresses under the old system, but the clock select options can't be mixed up, and here's why. Timer 0's clock select enumeration type is different from timer 2's clock select enumeration type. They're two separate types defined in two separate places, and as such, their values are incompatible. Enumeration values of one type don't convert into enumeration values of another type, even if they happen to have the same underlying bit patterns. So if the user tries to create a timer 2 object, but accidentally passes in a clock select option that goes with timer 0, they will get a compile error. Something that says the option that you specified is not a valid value of the kind of enumeration that I was expecting. And the user will see this and hopefully go and make the appropriate changes so that their code does what they had in mind in the first place. All right, so that was the two 8-bit timers. So that covering the two 8-bit timers got us to the point of having this traits table here. Now, we'd like to support all 6 of the timers. The other timers, though, are 16-bit timers. So there are additional things that we're going to need to deal with. First of all, we're going to need new rows for all of the new timers that we want to support, because all of these traits are still important for the 16-bit timers as well as the 8-bit timers. But there are also additional differences between the 8-bit timers and the 16-bit timers that we need to capture in some other way. So we'll need to add a trait to deal with that situation. So first off, let's fill in the new rows, add the new rows and fill in the existing columns. And so here are the address values for timers 1, 3, 4, and 5, and their associated interrupt mask registers. Again, the clock select options are the same for each one of these timers except timer 2, so they all have the common set of options. Okay, I see a question here. If you use placement new, then the first control register is going to be mapped to the base address of a timer, right? That means you can't add any more private members to that class because it would go to the hardware if anything is mapped beyond the last control register. Yes, that's correct. I'm going to answer this one live. The way that it's true that if you use this system where the objects are placed at the specific memory location using something like placement new or a class specific new that knows the location, then yes, you have to make sure that the data members in the type are specifically the hardware registers and only the hardware registers. If there's other data that you need to track associated with that hardware device that is not tracked in any of those registers, but is instead something you'd want to track in software, you would either want to use a different scheme to represent those things. So for example, I've been showing you a version of the code where, let me see, can I? Here, all of these fields are volatile uint 8t's. They're meant to just, because the timer 8t object is placed in the right location, they overlap with the predefined locations where those hardware registers are supposed to go, and you can speak to them as if they were, and you can just speak to them as if they were ordinary objects. An alternative approach would be to make these data members pointers to these registers, so that instead, and then you would not have to place your timer 8t object so that it overlaps those specific memory mapped locations. You would just write your timer 8t object so that its constructor fills in the appropriate values for the addresses of these types. And that might be, for example, another trait that you would have in place. Instead of the address that we had, we might have separate addresses for each one of these registers. That's another way of doing things that can also work. I'm demonstrating this approach because in my experience, I've had good luck getting good performance out of this. The approach of using pointer members, I haven't been able to fully test to get performance numbers I'm totally satisfied with on the Arduino yet. I've started my preliminary results I like, but I'm still working on that. But on the Evaluator 7T and some other boards I've worked with, this approach seems to be one of the ones that tends to give better performance. Okay, Bob question. What if you're not allowed to use new and delete, never ever, and you have to use the static stack way? Would this work? So yes, I mean, this use of new is not allocating memory. It's not going and fetching memory from the heap. There's no possibility that this function would fail. So it's not actually doing dynamic memory allocation. But I understand if some people say, yeah, but it's still the keyword new, and I don't want to touch that with a 10-foot pole. It's just easier for me to not use new than to tell people why this use of new is okay. That's fine. Yeah, you can use one of the other approaches that I was talking about, such as making the data members of our type pointers, or using, you can farm the work out to pointer to non-data member pointers, things like that. There are different options available. And this is what I was getting into when I said back towards the beginning that the thing that I want you to take away from this is that is this technique of capturing the differences between these two things in traits. And whether I use a version of the class that's placed in memory at a specific location, like I've been showing you in this talk, or whether I use one that has pointers as data members and finds those addresses in a slightly different way, the traits might be a little different, but the same basic approach works fine for creating an implementation that we have to maintain one body of code to support both timer 0 and timer 2, and as we're working on now, the 16-bit timers as well. I hope that answers your question. If not, feel free to sit down with me in Gather afterwards, and hopefully we can hash this out in a little more detail. Okay, so the address fields and the interrupt mask register locations, those look the same in our timer 1 traits and timer 3 traits and all the other new traits types. They're unchanged from how they looked in the traits objects that were just for timers 0 and 2. The clock select works a little bit different because now the values of the clock select enumeration are shared between timer 0 and 1 and 3 and everything except timer 2, which has its own special snowflake options. So it probably makes sense for those types to actually be using the same enumeration type. So what I'm going to do here is pull the clock select options that are shared amongst several timers out into its own separate type called standard clock select. And now when you look at most of the traits types, clock select will instead of being a complete enumeration type defined in there, be a type alias for the for a type, in this case, in most cases, standard clock select. Timer 0's clock select options are still unique to timer 0. We can just define the enumeration type in there. There's no reason to move those specific details elsewhere. Yeah. So we need to, so now, what more do we need to separate out our 8 and 16-bit timers? Well, we need to know, is the timer 8 or 16-bit, unsurprisingly? Because in our timer 8T type, up to this point, we had a few places where we were using uint8t as a type, and we were just assuming that that was the right type to represent the values stored in the timer's counter. And for 8-bit timers, that worked just fine. But for 16-bit timers, that count value could go up to 64K. We want to be that should be a uint16t in those cases. Oh, I see the a follow-up question there. Yes, could you place these objects via the linker file? Yes, depending, I think that would work. I haven't personally done that, used that approach myself in practice, but I believe I've heard of other people who have, and I believe it should work. So anyway, we have a new type, count T, that is our new trait to be added into our traits types, that is a type alias for whatever unsigned integer type we should be using to represent the timer's counter values. So timer 0 has uint8t, timer 1 has uint16t. And then in our timer class template, where before we had uint8t to represent a counter, now that will be an object of type count t. So before, the get count function looked like this. Now it's going to look something like this. It's going to return an object of type count t instead of type uint8t. This is another case of a dependent name. The type, what type count t is, depends on what gets filled in for the timer traits. So we want to preface that with the keyword type name to help the compiler understand what we're asking it to do in this situation. So that brings us to this iteration of the traits table, which now covers both 8 and 16-bit timers. It has the addresses for all of them, the separate interrupt mask register locations, and the bit size that we need to choose the right counter type for our timer objects. Now, there are other differences that we could capture, but this is the basic model that we build on here. We identify a difference, like the location of the timer, or what type of integer the timer uses to count, and we find a way of reflecting that difference between the different kinds of timers that we want to deal with as a member of our traits types. And as we follow that model, there's a pretty surprising amount of shared implementation code that you can write by following that approach. And it winds up being remarkably type safe, in part because it's built based on templates. As I mentioned before, the clock select enumeration for timer 2 is different. The user can't accidentally pass in an invalid clock select option for a timer that doesn't support that option. Moreover, the shared functions that we were looking at here were pretty short. They wouldn't, in a more complete implementation, they might not all be this short, but a lot of them would be fairly simple. And I would not expect many compilers to have trouble inlining these functions. So I would expect that you would get performance on par with what you would get if you just wrote these, if you didn't write these functions or classes at all and just accessed the individual register objects with handwritten code. Okay, that brings me to the end of what I was going to say. I can take some questions now, and I guess after that, we'll continue on into Gather, where you can speak to me a little bit more one-on-one. Do you have a technique for using these templated objects in higher levels without requiring those functions to be templated as well? Ah, I see. Yeah, what you're saying is, okay, but what if I want to write a function that can be written so that it uses whichever timer I choose, right? Where I could choose to use, say, timer 0 or timer 2, and I have other code written in terms of that. What could I do to, is there a way of getting that to work without making that other code templatized? And I think the only thing that comes to mind for me off the top of my head would be to, I don't think it would work with the placement technique that I'm showing you here. You would need to use a different implementation, like having the data members be individual pointers to the registers. But if you did that, because it doesn't have to match the layout of the memory mapped space exactly, you could make the member functions of that template type of virtual. And then you could use a common base class type for all of these different timers to call virtual functions that do what is conceptually the same thing, but yes, but without needing to specifically say it's timer 0 or timer 2 or timer 3. That's the only thing that comes to mind off the top of my head. Oh, you mean using a pure common abstract class as a parent class? Yeah, let me see if I can, let me pull up an editor here. What I was imagining was that you would have something like a class basic timer Yeah, that would have, say, where the yeah, in this case, this is interesting. Okay, depending on what this is going to be harder or easier to make work, depending on what exactly you're trying to do with it. Because for some functions that you might want to write, this would work just fine. You could, for example, it would be relatively easy to write, say, a pause function or a resume function for a timer like this, that then and then your template creates you would be able to do something like that and implement those member functions there. But if you're talking about something like the get count function, that winds up being a little bit tricky because, well, what do you want to be the return type here if you're going to support both 8-bit and 16-bit timers? You could either you specify some large type and just expand it up, or you might find yourself doing something like having a basic timer type and then a basic timer 16 type that's derived from basic timer. That then has its own get count function. Yeah, yes, as some points out in the chat, yes, this could be, instead of making this a function that returns a uint 16t for basic timer, I could instead do something like make this a function that returns a variant, which you have a lot of options here. It depends on, I think that it depends a lot on how much you want to obligate the user to do versus how much you want the type to do for them and be checked and have that stuff all checked at compile time.